Given the following function, f of x equals 3 plus x if x is between negative 3 and 0, f of x equals 3 if x is equal to 0, and f of x equals the square root of x if x is greater than 0. So we have a piecewise defined function with 3 pieces. So over here, each piece has its own domain. So in part A, we want to find the domain of the entire function. So we need to identify the domain of each piece here, which is listed right here. So if we put all these together, this is the domain of the entire function. So just to help you visualize and start thinking left to right, again, these generally go left piece, middle piece, and right piece. So we've got left, middle, and right. So our left piece, if we look at the domain here in the inequality, it goes from negative 3 to 0, not including 0. So if we wrote that in interval notation, we'd have negative 3 with a bracket because of the equals on the inequality, comma 0 with a parenthesis because there's no equals here on this inequality. Now if you look at this middle piece is actually just one point. When x is 0, it's not a range of values between two different values, it's just x equal to 0. This is actually an ordered pair. The ordered pair, x value of 0 and a y value of 3, 0, 3. So the domain of this piece is just at the point when x is 0. Then the domain of the right piece is x greater than 0. So again, just to start your brain going the left to right, interval notation is a great way to view domain left to right. So we know it doesn't include 0, so we put a parenthesis, comma, infinity. So this was x equal to 0. So if we join all these together, moving left to right, those all together give us the domain of the whole function. So you want to go to the left piece first and the left boundary of that piece. So the left boundary of the left piece is negative 3. So on our domain here, we want bracket negative 3. Then this piece goes all the way to its right boundary of 0, not including 0. But then we jump up to the middle, and that fills in. This would be an open boundary, an open circle when we sketch that boundary. But then this point, at x equals 0, it would fill in that gap in the domain here, so we'd include 0 here. And then once we move left to right, we move just past the 0, from 0 to infinity, we'd have the right piece. So if you put all these together, it's just bracket negative 3, comma, infinity. So when they want the domain, they want you to join all the pieces together, the domain of each piece, and put them together. And we typically want interval notation, and we'll tell you if we want it in another form. Okay, so now we have intercepts. So we should be intercept professionals at this point in our algebra careers. So if we want to find intercepts algebraically, so we'll do our x-intercepts. And I say plural. It could be plural because we could have multiple x-intercepts in a function. So what we need to do is test each piece and see it, because each piece could have its own x-intercepts. So we look at the left piece here. It's a 3 plus x graph, so we know that's a linear function. So we want to see, does this line cross the x-axis in this range from negative 3 to 0? This line could cross it in a different location outside of the range of this piece, but we're snipping a little piece of this line between negative 3 and 0. So what we'll do is we'll plug in a 0 for our y value, so we know we have y equals 3 plus x from the definition of the function. So if I put in a 0 for my y and solve, I get an x value of negative 3. So that means this line, 3 plus x, crosses the x-axis at negative 3. So we want to see, does this piece of the line include the x value negative 3? Well, yes, it does, because that's actually the left boundary. So that means that this left piece will have an x-intercept at negative 3, 0. So there's one of our intercepts. Now, if you remember, oh, and we might want to note the shapes here. So we know that this left piece, this is linear. Now this middle piece, because the domain is just one x value, this is actually just an ordered pair, 0, 3. So that middle piece is just an ordered pair, 0, 3. So obviously 0, 3 is not going to be an x-intercept. So we don't need to do anything there. And then we look at our right piece. So our right piece is a square root of x function, square root function. So now we want to plug in a y value of 0 into that function. So we have our y equals radical x. So if I put in a 0 there, and if I solve this equation, so we know to solve our square root equations, we'd square both sides to take off that radical. So then we'd have x equals 0. So that means, and we should actually know this from the general shape, the shape of our parent function, the square root of x, it has an x-intercept at 0. So this square root function is going to cross the x-axis or intersect the x-axis at x equals 0. But now we have to look, is the x value of 0 in the domain of this piece? So this piece doesn't start till just past 0. So since this is not in the domain, this is not going to be an x-intercept. So we can just cross this off because it's not in the domain of the piece. Okay, so now we want to look at our y-intercept. And remember, we know we can only have up to one y-intercept in a function, because remember, functions have to pass the vertical line test. If you had multiple y-intercepts, you would fail the vertical line test. Okay, so we're going to plug in an x value of 0 into the appropriate piece. So with the x-intercepts, remember, you have to check each piece potentially to see if there's x-intercepts there. But for the y-intercept, there can only be one, and the domain's going to tell us. So the only place where x equals 0 is that middle piece. So that middle piece, that ordered pair, that is the y-intercept. So our y-intercept is just our point 0, 3. So when we go to graph this, those intercepts are obviously going to be very, very useful points to plot. And actually, we can plot those right now just so we don't forget. So we've got the point -3, 0. And I'll label these. Please try to remember to label them. And we've got our y-intercept 0, 3, 1, 2, 3. Okay, so now when we go to graph, if you remember from the steps that we talked about in the previous video, we want to find for each piece left, middle, and right, and I encourage you to move left, middle, then right. Do the left piece, then the middle, then the right. So for each piece, we've got to plot at least the boundaries of each piece and then connect with the appropriate shape. So we know our left piece here, our left piece, it's linear, the y equals 3 plus x. So we're going to make an xy table here. So it's y equals 3 plus x from the definition of the function. Okay, so if we look up here, we see that the boundaries of this piece are -3 and 0. So I have to plot at least those boundaries, and oftentimes that's sufficient, but you have to at least show me those. So we've got -3 and 0. So if I put a -3 into this function for x, 3 plus -3 would give me 0. And then if I put a 0 in for the x value here, 3 plus 0 is 3. And these actually should look familiar. These actually happen to be our intercepts, which we found above. Won't always happen, but it did happen here. Okay, now it's important to note that this right boundary of this piece, the 0, did not have an equals on it. So we do not include that boundary. That means when we plot the point 0, 3, in this boundary, it's actually a hole. So you want to note that. This is actually a hole in the graph, and we'll indicate that with an open circle. Okay, so if we go onto our graph, we actually, again, in this case, we actually happen to have these plotted already. We've got our -3, 0 as the left boundary of that piece, and then the right boundary is 0, 3. But now notice, we already plotted the intercept, 0, 3, from the middle piece. So if we were to plot 0, 3 here with an open circle, this 0, 3 from the middle piece actually fills it in. So we can actually just connect these and make a line for that left piece. So technically there'd be an open circle here from the left piece, but then when we move to the right to the middle piece, that ordered pair 0, 3 actually fills it in. So that will happen frequently. Sometimes you won't actually see the holes in the graph, but just note that would be a hole from that left piece. So we'll just note here our middle piece. That was the ordered pair 0, 3, and it filled in this hole. Okay, so then we continue and move to the right piece. So if we look above at our boundaries, our right piece, the left boundary of our right piece is 0, and the right boundary, it's infinite. It doesn't have a boundary. So when we go to plot this, and we make our xy table, so now we have y equals square root of x, we have to show the 0, and then since we don't have a right boundary, we'll have to just show an arrow when we sketch it to show that it increases, it goes infinitely to the right. So then just pick at least one other point to the right of the 0. So a convenient point, since we're plugging into a square root function, would be a perfect square, so something like 1 or 4. I'm going to put a 4 on here, but any other point to the right will be sufficient. So if we plug the 0 into our square root function, the square root of 0 is 0. And if we plug in our 4 into our square root function, the square root of 4 is 2. Now we want to note that this left boundary of this piece, there's no equals here, so it's not included. So that means when we sketch this, this is also going to be a hole. We'll represent it with an open circle. And then I think it's important just to note in your table, I like to put like an infinity symbol here, just to remind myself that when I sketch this piece, I have to show an arrow indicating that it goes infinitely to the right. And that's something I'll be grading. I'll be checking on tests and quizzes that you show me that right boundary, which is infinite. Okay, so I'll sketch this right piece here with another color. So the left boundary of my right piece is 0, 0, so I'm going to put an open circle. And then I've got the point 4, 2. And now I know that the shape of a square root graph is that increasing ramp looking shape. So I'm going to connect it with the appropriate shape. So if you were to incorrectly connect these with a line, make it linear, that would be incorrect and you get points off on a quiz or a test. So make sure you're showing the appropriate shape, that appropriate curve, and the arrow, I'll also be checking for that. And that's why I like to put the infinity in the table here, to remind myself to put the arrow. And then we'll label these points. So we had 0, 0, 4, 2, and then we've got that arrow nice and clear so that we know that that extends infinitely to the right. So as you look at this, the definition actually had 3 pieces, 3 parts to it, but when you look at the picture, the final graph, it actually only looks like 2 pieces, because remember that left piece, that line, there was a hole at the end of it, but the middle piece, the 0, 3, filled it in. So it's like the middle and the left piece connected. So visually it just looks like one piece. Okay, so now we have our graph, and we can look at our graph and determine if this function is continuous on its domain. So we remember continuous. So that means as we trace the graph left to right, are we able to sketch it? Would we be able to trace left to right without picking up our pencil? So I start all the way left, and as I trace left to right, I'm good until I get to here, and then I'd have to pick my pencil up to jump down to this hole. So because I'd have to lift it, this is not continuous. So no, it is not continuous on its domain. And then once we have the graph, we need to be able to identify the range. So again, we should be domain and range professionals at this point in our math careers. So we want to name the bottom and the top boundaries. So we want to start at the bottom of the graph, the lowest point. So the lowest y value that I see is a y value of 0. Now note, it's not included here in this piece, but it is included in this piece. So that means I will use 0 in the range of my piece. I will include it. So then I can put a bracket 0. And then as I trace up, this piece would stop at a y value of 3, but remember this arrow means this continues infinitely, and we know that a square root graph, it gets higher and higher. This pattern extends, so there's actually no limit on its range here. It just goes higher and higher, so we know that our range will be from 0 to infinity.